Want to get started for the 17th Annual Mars Society Annual Convention. We're going to get started with Dr. Robert Zubrin. We'll get started with Dr. Robert Zubrin on how we can reach Mars. Dr. Zubrin.
Thank you. I'd like to welcome you to our 17th convention in Houston. We chose Houston this year because we anticipated that the Orion capsule would be launched for the first time shortly after the conference, and that is now scheduled for December. So the world's eyes are going to be turned towards Houston this fall. But and returning the United States to manned space flight is, of course, a very useful step towards getting back to Mars. But it doesn't, in itself, get us to Mars. And we haven't been going to Mars for quite some time. The problem, as I see it, is that the fundamental method of operation of our space program, and in particular the manned space program, has been deeply flawed for the past 40 years. It was not deeply flawed before that, and quite the contrary, and therefore produced astonishing results. So what was the difference in the way NASA operated during the Apollo period and the way it has operated since? The first answer that many people come up with is, well, NASA had much more funding during the Apollo period than now, so naturally they could do much more things. But that, in fact, is not true. It's not true at all. If you take NASA's funding from 1961 to 1973, that is from Kennedy's speech initiating the Apollo push to the moon, down to the final Apollo Skylab missions, if you take all that money, translate it into today's dollars, and divide the sum by 13 years in question, you come out to $20 billion per year in today's money. NASA's budget this year is $17 billion. So while NASA's funding this year is a little bit less than its Apollo average, it's not substantially less. It's not a factor of 4 or a factor of 10 less. It's 15% less. And there have been years since 1990 to the present in which NASA's budget in inflation-adjusted dollars was actually greater than its Apollo average. NASA has spent as much money in real dollars from 2000 to today as it did from 1961 to 1973. Okay? That's amazing. If you think about the fact that from 1961 to 1973, NASA not only flew Mercury, Gemini, Apollo, and Skylab, okay, but they also developed hydrogen and oxygen rocket engines, multi-stage heavy-lift launch vehicles, in-space life support systems, spacesuits, interplanetary navigation techniques, interplanetary communication techniques, propulsive soft landing techniques, re-entry technology, RTGs, substantial amount of development for nuclear rocket engines. They flew 40 lunar and planetary robotic missions. That is, in terms of both technology development and missions performed, they vastly outperformed the same period of the past 14 years, in which we flew, I think, about actually 40 shuttle missions, and they did substantial construction on the International Space Station, and they did a couple of repair missions to Hubble, and they did about a dozen planetary probes, but no significant technology development. And this is particularly peculiar when, in fact, the justification for not having a focused program like Apollo that was given by both Administrator O'Keefe and also Administrator Bolden is that we want to have a technology-driven thing in which we work on developing technologies and then the ability to go anywhere, anytime will materialize after these technologies appear. And in fact, there's been no substantial technology development, certainly not remotely comparable to what happened during the Apollo period when they were focused. So what's the difference here? Okay, the difference is that when you actually have a mission, when you are mission driven, okay, then the mission calls forth a plan for the mission, which calls forth vehicles, which requires technology, which then must be developed, and developed not just at the bench scale, but all the way to flight status. If, on the other hand, you have a so-called technology-driven program, what you really have is a constituency-driven program, where various factions in the various technical communities are pushing their own favorite technologies, which may have merit or may not, but it doesn't matter whether they have merit or not. What's actually sustaining them is the constituency support, okay? And if political straits oscillate, the support for a particular program disappears, and it almost never reaches flight status. It's almost always thwarted, and you get this repeated fits and starts. So you don't get the actual mission to the goal, and you don't get the technology development either. So the way I view it, if you compare the Apollo mode to the post-Apollo mode, you compare it to two couples each trying to get their own dream house. Couple number one, they think of what the house should be, they work it out, so I live with the house we want, they bring in an architecture, he designed the house and brought outlines. When that's done, they bring in a builder who actually makes the blueprints, and then they order the parts, they build the house, and they have the house. That's the Apollo mode. The other couple, what they do is they spend their weekends cruising garage sales for house parts. Okay? And they buy whatever parts appeal to them at the moment. And they pile them up in their backyard. You know, some Doric columns, some aluminum siding, a spiral staircase, you know, a fountain with a statue of Napoleon in the center. And they pile the stuff up in the backyard. And then the in-laws come and visit, and pa-in-law says, "Why do you have all this junk in your backyard?" And, you know, they say, "Well, it's for our dream house." And he looks at it, kind of cross-eyed, and says, "I'd like to see the plans for this dream house." And so they hire an architect and they say, "We want you to design a house, and it has to include all of these parts." So the plan is developed, but it's not a plan that is designed to be implemented. It's designed to provide a rationale for the purchases that they have already impulsively made. So the house is never built, and but nevertheless they are defended from criticism from their relatives. And that's, you know, the current situation. Recently, there was actually a report by the National Research Council that criticized NASA's current mode of operation. And I don't fully agree with this report, as I'll explain, but I agree with its main point, which was the point that I just made. Which is that you can't get anywhere with this constituency-driven methodology. I mean, we did not reach the moon because one day in 1963 a bunch of guys ran into each other in the cafeteria at JSC or Marshall or someplace, and they said, "You know, with your lunar ascent vehicle, my booster, his capsule, and his lunar landing system, if we put these things all together, we could send people to the moon and back. What do you think?" No. All these things came from the plan, okay, and that's why they all fit together, okay, so nicely. You know, so they criticize this, but you know, here you have the asteroid retrieval mission, which got into the program through various means that would require expertise in psychology, but okay. But then someone comes. Oh yeah, it was actually put in to justify a focus on developing electrical propulsion. They wanted to give electrical propulsion a mission. And they go, "Oh, here's a good mission for electrical propulsion: move a 500-ton rocket into lunar orbit." And then they had to think of a reason for that mission, so recently they started talking about going to Phobos. Well, exploring a rocket lunar orbit would be practice for going to Phobos, okay, which supposedly is a key move towards sending humans to Mars. Now, actually, basing on Phobos is not useful for sending humans to Mars. Okay? If you put a constraint on the human Mars mission that it must go to Phobos before it goes to the surface, you add about 2 kilometers per second of delta V to the mission on the downward leg, and then if you must go to Phobos on your way back, you add another 1.5 kilometers per second to the mission on your return leg, adding 3.5 kilometers a second, which is a catastrophic addition to the propulsive requirements of the mission for no particular purpose. And that is, by the way, if you confine the mission to going to the Martian equator. Phobos is in an equatorial orbit, and the only convenient place to go from Phobos is the equator. If you actually try to go somewhere else, then it's much worse. Okay, so now here you have, to justify a to justify electric propulsion, we get an asteroid retrieval mission. To justify the asteroid retrieval mission, we stick Phobos into the Mars architecture, which actually impairs the Mars architecture. Okay, and so it's questionable whether any of this will really happen, because this is only being sustained by current alignments of the factions, various years in various places. If you want to go to Mars, you've got to go to Mars. And if you want to develop a technology that will actually take you to Mars, the way it comes is the technology doesn't develop by itself, and then eventually you have the capability to go to Mars. You decide you're going to go to Mars. Okay, you work out a plan for doing it, the most efficient, coherent plan you can, and then those technologies to implement that plan get developed. That's how you go to Mars. So, what's my plan? Many of you have heard it before, but it's my story and I'm sticking with it. Okay. The plan that I believe is the correct way to go to Mars is known as Mars Direct. Okay. It is accomplished using direct launch to Mars with heavy lift launch vehicles in the class of the Saturn V. Okay. When we developed this in 1990, shuttles were still flying, so we designed this to be built out of shuttle technology. So we designed a heavy lift launch vehicle. This was when I was at the Martin Company. There we go. So we designed a heavy lift launch vehicle based out of shuttle stuff. Here's the external tank without the ogive pointy top. We don't need that. Pod of force shuttle main engines, which we offset in this odd way because we were going to use the shuttle launch pads, which have the flame trenches positioned here. A couple of solid rocket boosters, and then a hydrogen-oxygen upper stage with 250,000 pounds of thrust, which is the same thrust that powered the J2 engines that drove the upper stages of the Saturn V. And then on top of it, a spacious fairing 10 meters in diameter, or 33 feet if you work at Lockheed Martin. Okay. Now, this booster, which is not too dissimilar from the SLS that is currently being developed, of course, they put the engines underneath as they should, because we're not trying to launch with the parallel shuttle. But this could lift 120 tons to low Earth orbit, which is pretty good. You know, the shuttle could lift about 20, Titan IV could lift 20, Ariane could lift 20, Proton could lift 20. There's 120, which may seem therefore like a fantastical number, except if someone recalls that the Saturn V could lift 140. Okay. So we in the space program are somewhat in the condition of Italians around the year 800 AD wandering around the rooms of imperial Rome and looking at the gigantic temples and coliseums and aqueducts and saying, we once built that. Who could have built that? Nobody could have built that. They must have been gods who built that. Okay, we couldn't build that, but we did build that. And once upon a time, we built boosters with this sort of capability. But in addition to launching 120 tons to Earth orbit, what this vehicle can do, because it has this upper stage, it can use this upper stage to throw payloads far beyond low Earth orbit. It can throw 47 tons on a direct trajectory to Mars, or 59 to the moon. And that's how you want to do the mission. Just lift and throw and let it go. Send the payload to the planet with the same booster that launched it to orbit in the first place. That's how we've done every real planetary robotic mission. That's how we did the Apollo missions to the moon. And if you can do the human Mars mission in that way, just lift and throw it, shoot the payload there, right there you've gone 90% of the way towards taking the Mars mission out of the world of the science fiction creature and putting it in our world of real mission engineering. But how can we do that? Most of these Mars mission designs that you see have masses of 600 tons or more, which is to say at least 4 times the capacity of a Saturn V booster to put into orbit. And so you can't do that. You blow away Orlando when you took off. It should damage morale, decay. And so you could split the mission, but you really don't want to split it up into 4 parts or 6 parts, because if you have 6 launches and they're all mission critical and one goes in the drink, you lose the whole mission. Okay, now I and a fair number of other people am willing to divide the mission up into 2 parts and hope that 2 launches will both work. Okay, but still that would leave us much too much for a launcher of this class. So what else can you do? Well, you have to ask yourself, why are these Mars missions so massive? Well, it turns out the majority of the mass that they're sending to Mars is the propellant to come home. Well, doesn't it seem rational to go to Mars with the propellant you need to come home? Well, it may be convenient, but is that how we've really explored on Earth? Did Lewis and Clark attempt a 3-year transcontinental round-trip mission of exploration, bringing with them all the food, water, and air they would need for themselves and their horses? No. If they had done so, they would have needed a wagon train and supplies for every man and every horse. And the wagoners and the wagon horses would have needed further wagon trains. And they would have needed further wagon trains. So in fact, it would have gone exponential. It would have blown the budget of Thomas Jefferson's America. In fact, it might have exceeded the mass of the Earth. But that's not what they did. They hunted their way across. And to a certain extent, they obtained supplies by trading with Native Americans. But in either case, they were making use of the resources that were available in the environment they attempted to operate in. Okay? So why are we going to Mars? We're going to Mars because Mars is the planet that has on it the resources needed to support life and therefore technological civilization. Well, if you can make intelligent use of those resources, the same resources that make Mars interesting are also what makes it attainable. So what is the travel light and live off the land approach to Mars exploration? Okay. There's the mission sequence chart. Okay. So in a given year, we use this booster to throw one of these, a Earth return vehicle to Mars with no one in it. It's unmanned, it's unwoman. This goes to Mars on a minimum energy trajectory, 8-month transit. It goes to Mars, it aerobrakes into orbit on Mars, and then we land it on Mars. Okay. Now, what is this thing that we have landed on Mars? It's what I said. It's called the Earth Return Vehicle. It has a small cabin here suitable for a group of 4 people to take a 6-month transit back from Mars to Earth in the final leg of the mission. However, no one is in it now. Then you've got 2 methane, oxygen, chemical propulsion stages here, which, however, are unfueled. Now, when we first designed this mission, we were going to make methane, oxygen. Mars' atmosphere is carbon dioxide. So there's your carbon and your oxygen. You still need hydrogen. We decided we would bring the hydrogen with us in the lower stage tanks of this vehicle. And you can do that. Okay. Now we know that there is water present in Martian soil. Even in the equator, in many places, 5% concentration in soil, and in many places much more than that. And that brings up the option of extracting water from the soil to get the hydrogen. But I'm going to, for at least the purpose of this talk, let's stick with the idea that we're bringing the hydrogen with us to Mars in some of these lower stage tanks. Okay, this is landed on Mars, and then we've, not shown in this diagram, is a light truck, like a little pickup truck. It's got a small nuclear reactor in the back, about 100 kilowatts. 100 kilowatts is like 130 horsepower. So it's the same amount of power that powers a medium-sized car in this country. And So we're not talking about a giant nuclear power plant that powers a city. We're just talking about a nice little putt-putt nuke sitting in the back of the truck. And then after this is landed on Mars, the truck, which by the way is driven by methane oxygen, is telerobotically driven a few hundred yards away from the landing site, and then the reactor is lowered off the truck, and as you're driving, unwind a cable off the back of it, and then you put the reactor on the ground, preferably in a little crater or a ditch or on the reverse side of a hill, anything to put a nice sized chunk of dirt between the reactor and the main landing area, and then you turn it on and you got power to ship. And what you do then is you run a pump, and you suck in the Martian air, which is carbon dioxide, and you can react that with hydrogen. In the presence of the catalyst, these will react and they will produce methane, CH4, that's excellent rocket fuel, you store that in your tank, and then water. The water can be electrolyzed, split into hydrogen and oxygen. Oxygen stored in your tank, that's your oxidizer to burn the methane with. The hydrogen is recycled to react with more carbon dioxide. And then you have a third reactor in which you take carbon dioxide and you just split it into carbon monoxide and oxygen. The oxygen you store as a useful oxidizer, the carbon monoxide you can dispose of as waste. You can do that on Mars. There's no EPA there. That's one of the main reasons why people want to go to Mars. And by the way, this reaction here, this third reaction, is going to be demonstrated on the Mars 2020 rover. The decision to do that was announced just this week. So this part of it will be demonstrated there. The other parts of it have, the other two parts actually are very well-known chemistry, and they've been demonstrated as integrated system in the lab by myself, among several other groups. It was demonstrated at Lockheed Martin, it was demonstrated at Pioneer Astronautics, systems have been built at JSC and elsewhere, and it's a very well understood cycle known as the Sabatier electrolysis system. So now you have a full, well, it took 8 months for this to fly to Mars. It takes 10 months to make the propellant, assuming you have 100 kilowatts available. So now you have a fully fueled Earth return vehicle sitting, waiting for you on the Martian surface. That being the case, at the next launch window, because you have a launch window to Mars every 2 years, okay, you launch 2 more boosters off the Cape. One shoots out another Earth return vehicle fuel factory system, the other shoots out a habitat with a crew of 4 astronauts in it. Now, we have our return ride waiting for us on Mars. So we do not need to fly to Mars in some gigantic Death Star spaceship. We don't even need to fly to Mars in a comparatively modest Millennium Falcon. No, we can fly to Mars in a tuna can. And this is very advantageous. They've been proven in commercial tuna industry as excellent packaging systems. Ours are somewhat larger than the chicken and the seed model. This is about 27 feet in diameter and 16 feet tall. So it's got 2 decks, each with 8 feet of headroom. The upper deck is where they really live. The lower deck is more of a garage, cargo hold, workshop kind of place. So here's one potential layout for the upper deck of the HAB. And what you see is a little stateroom for each of 4 astronauts, a science lab, exercise area, the water room, the table where you eat and play cards and you sit around and talk. And in the center here is a solar flare storm shelter. Okay? Now this is worth talking about. There's 2 kinds of radiation that can get you in interplanetary space. There's solar flares, there's cosmic rays. They're different. Solar flares come from the sun. They come in an unpredictable way in a gigantic rush. You might get a big one about once a year. They can deliver several thousand rems of radiation to an unshielded astronaut, which is enough to kill, either immediately or after a fairly brief period of radiation sickness. That's bad. The good news, however, is that kind of radiation, solar flares, are basically protons with energies of about 1,000,000 volts. And that kind of stuff can be stopped by 5 inches of water, or things that from the nuclear point of view are essentially the same thing as 5 inches of water, such as food, or things that water and food become as the mission proceeds. And we have enough of that on board to pack it in around a limited central area and create a shelter. So solar flare happens, the alarm bell rings, everybody goes in here, you're in stuck tight in here, just like wires on the New York subway, except there's no solicitors coming through, for a few hours, and then the all-clear rings and you leave, and that's how you're safe against solar flares. Now the other kind of radiation, and the one that's getting most of the press nowadays, although some people sometimes confuse solar flares with it, is the cosmic rays. Now they're particles, they don't come from the sun. They come into our solar system from interstellar space. And actually, how they are created is a little mysterious still, because they come in with energies not of millions of volts each, but billions of volts each. That is 1,000 times more energy particle for particle than a solar flare particle. And therefore, it's not clear how they could be created because nuclear reactions don't have that much energy. Okay. But nevertheless, they certainly exist. They come in, and you couldn't stop them with 5 inches of water. They'll just punch right through that. Okay, so you're going to take that dose. All right. However, the magnitude of that dose is around 50 rem, that's half a sievert, for every year in your interplanetary space in the Earth, Mars regions of the solar system. And okay, I'll get to it later. And what is that? That is about 0.5% risk of getting cancer at some point later in your life. Okay, and as I will show you, by the way, somewhat later in this talk, that that cosmic ray dose has already been received by 6 astronauts and cosmonauts who have done extended stays on the Mir or the International Space Station with no radiological fatalities among that group, none. Nor would you expect there to if you had a risk factor of 1% and 10 people, the odds are 10 to 1 that no one will have succumbed. And they haven't. So, you know, there are people saying we can't go to Mars because of this cosmic ray risk. This is a modest portion of total mission risk. Shuttle program, not on the basis of calculations, but on the basis of the facts of its record, was a 2% risk of getting blown up. Okay? Yet, I mean, how many people here would ride on the shuttle if they gave you a chance? I think most. Most people would jump at it. The flight risk of a Mars mission, because it's significantly more complex than a shuttle mission, is going to be higher than 2%. So a 1% risk of cancer is not a major part of overall mission risk. And there are people who say we cannot or should not go to Mars until we can go much faster to reduce this risk. Well, that is wrong, okay? And I'll tell you why it's wrong. Because let's say you had a superior propulsion system like nuclear thermal rockets that could, in fact, reduce the flight time significantly. How long should you take to go to Mars? Should you go to Mars as fast as you can? No, because there's a trade-off between how fast you can go and how much payload you can take for a given launch mass. Right? So you do reduce certain kinds of risks by going faster, but at the same time, you're reducing the total payload, which means the redundancy, for example, of your life support system, things that you're going to depend on. Okay? So now it turns out that if you pour on the propulsion, you can cut the flight time from the canonical 8.5 months, which is the minimum energy transit, to 6 months without taking too much extra propellant, or another way, without reducing the payload by too much. Okay? So 6 months is the right answer. Why is it 6 months and not 5.9 months or 6.1 months? Okay, why is it 6 months? The reason why it's 6 months and not 5.9, 5.8, or 6.2 is because the 6-month transit out to Mars is also the free return orbit to Mars. That is, if you go to Mars on that 6-month trajectory and you decide to abort the mission, you can coast past Mars, go out to the about 2 astronomical units from the sun, and come back, and you will reach the orbit of Earth exactly 2 years after you left. And so Earth will be there when you get there. And that's an important abort option. And it is unique for that, and that makes the 6-month orbit uniquely advantageous. It also happens to be about where the mass trades out, and then in terms of keeping most of your payload mass and shortening some of the triple transit time, but then you preserve that. If you try to go to Mars faster than that, if you try to go to Mars in 5.5 months, it will take you longer to coast back around and reach the Earth, and the Earth won't be there when you get there. So there's that. Now, while we have not experienced radiological casualties in Earth orbit, we have received physiological damage from another phenomenon entirely, which is zero gravity. deconditioning of astronauts. Now, it only takes 6 months to fly to Mars with our current propulsion, and 6 months is a standard rotation on the space station. So it's not like you can't do the mission if you accept zero gravity weakening of the astronauts for 6 months. But we are going to Mars to explore, and exploring requires physical activity, including hiking long distances over unimproved terrain wearing heavy spacesuits. You want people to be physically fit when they get to Mars. So what is the answer to that? The answer is artificial gravity. And this is a doable thing. In this mission, we can create artificial gravity by tethering off the burnt-out trans-Mars injection stage. This tether is 1.5 kilometers, about a mile long. Spin this up at 1 RPM, we can create Mars gravity in the ham. If you spin it at a little less than 2 RPM, you can create Earth gravity. But what they need is to be ruthlessly more spared, to do the minimum technology development, have the minimum key technologies, and scale the size of the mission to the hardware available. And you know, if you don't like my super minimal Falcon Direct thing, do it with SLSs. Okay, fine. You'll have more mess. You can even do mate and dock 2 SLSs. Okay, but don't include NTR. And I say that even though I'm very much an NTR supporter, because you don't have it, and you're not going to have it in 8 years. And if you make the mission dependent upon that, you're basically saying you can't do our mission. You can say we should have a parallel development program to work on NTR, and once it's available, we'll be able to increase the size of the crew from 3 to 6, or whatever, because your trans-Mars injection mass will double. But design the most doable mission. Other questions?
Do you have
What?
Do you have a mission cost estimation of your proposal?
Yeah. Well, when we designed the Mars Direct plan back in the early 90s, we came out with a development cost of $20 billion to develop these hardware elements, and then about $2 billion for each Mars mission by the copy, and $1 billion for each lunar mission. And so that if you did a 20-year program in which the first 10 years you were developing all the hardware, and the second 10 years you were flying 10 missions to the moon and 5 missions to Mars, it was $40 billion. Now, that was a tremendous variance with the 90-day report, which projected $400 billion. However, NASA, as I mentioned, in Design Reference Mission 3, they adopted their own version of Mars Direct. That's what I call the semi-direct mission, the 3-launch architecture. Okay, it was 3 launches instead of 2. It was crew 6 instead of a crew 4. They had more equipment, they had heavier equipment, but they stuck with the principles of direct launch to Mars, no on-orbit assembly, no need for additional orbital infrastructure, long duration stays on Mars starting from the very first mission. That's extremely important because the short duration missions involve much greater propulsion requirements and are much harder to do. And use of in-situ propellant starting on the very first mission, as opposed to developing a much heavier hardware set without in-situ propellant and then introducing it later, which misses the whole point of avoiding development costs. So they did those 3 things, and they came up with a program that included development of all the hardware for the Mars mission and flying 3 human missions to Mars. And their estimate was $55 billion. Now, so we were at 40, they're at 55. They had a crew 6, we had a crew 4. We did some lunar missions, that was not included in their program. But the issue was not those differences. As Carl Sagan said to me at that time, when he saw that, he said, look, the issue is not whether it's 40 billion or 50 billion. The issue is that it's tens of billions, not hundreds of billions. Okay? That's the fundamental issue. And in other words, you know, the V-22 tilt motor aircraft, a medium-sized military procurement, was a $40 billion program. So there's any number of federal government programs that cost $40 billion that no one in this room has ever heard of. So if the mission can be done, if the program rather can be done for 30, 40, 50 billion, then this is a doable thing. Now, I think actually if these SpaceX elements are brought into the discussion where a significant chunk of the development will have been done, and also flight costs are fairly low, then the costs can even be brought down. I do not believe that humans to Mars has got to be a $400 billion project or a $200 billion project or even a $100 billion project. I think it can be done for tens of billions. In the back.
Robert, I've disciplined myself to think in terms of millisieverts, and you've got REMs up there. I used to think in terms of rads and REMs. Could you tell us basically, I mean, what is the chart you had that was in REMs? What is that to equate to a millisievert? Because I don't think in those terms anymore.
Okay, a sievert is 100 rems, so a millisievert is a tenth of a rem.
Okay, so they're at how many, the maximum over there was how many millisieverts?
Well, we were at 60 to 100 rems, so that's 600 to 1,000 millisieverts.
Okay. What's going on with the lawsuit that Elon has against the government over the launching of
Okay, well, I'll have to wind up at 10 o'clock, but that's still underway, but I think he's going to win, primarily right now, because of the breakdown with Russia, which makes the Air Force position impossible. It's no longer a plausible position. They cannot make U.S. reconnaissance satellite launches dependent